Welcome. We want to take a look at an example of finding a relative growth rate model from the doubling time. So we have a population of rabbits that doubles every 20 months. That's going to tell us a piece of information a little bit later down the line, right? Kind of like in the previous example, we saw what a population was 20 years later. Actually, it was currently, and we wanted to find out what it was 20 years ago, but it's the same idea. We have an initial population of 50 rabbits. So in this case, we're not looking for that initial population. Rather, we want to find the relative growth rate so we can write that relative growth rate model. So we're working in years here, and the doubling time was given in months. So one thing that we're going to want to do is we're going to recognize that the doubling time in years should be 20 months divided by 12. We can simplify that common factor of 4 there. So 5/3 years. That's the number we'll use for doubling time. We know that the model, relative growth rate model, A of t, is going to be P times E to the RT. And in this case, we have an initial population of 50 rabbits. We also know that A of 5/3, since the doubling time is 5/3 of a year, I know that I will have 100 rabbits after 5/3 years. So this is equal to 50 times E to the R times 5/3, and that's going to be 100. All right, divide both sides of our equality here by 50 to get E to the R times 5/3 is equal to 2. And now we have an exponential equation, so we can just rewrite in logarithmic form. The natural log of 2 is equal to R times 5/3 multiplied by 3/5 to get 3/5 times the natural log of 2 is equal to the relative growth rate. So our goal is to find the relative growth rate model, and we can write it as A of t is equal to 50 times E to the 3/5 natural log of 2 times R. Times T. There we go. And that's it. Now, it might be the case that you want to evaluate 3/5 times natural log 2 and round to some number of decimal places, and that would be perfectly fine. That you might feel that that looks a little bit better. Again, if you want to do that, no problem at all. What you might notice, for those that are interested, we can write this as 50 times E to the 3/5 t, 3/5 times t, and that thing, I'm sorry, I didn't want to write it as 3/5 t. I wanted to write it as natural log of 2. There we go, natural log of 2 raised to the 3/5 t. Because when I take a base to a power and then raise it to a power, I multiply those two exponents. So this is equal to that. But e to the natural log of 2 is just 2. So this is 50 times e. Sorry, not e, but 50 times 2 raised to the 3/5 t. And if you want to take it one step further, you could observe this as 50 times 2 to the t divided by 5/3. Why is that useful information? That's useful information because we can recognize that if we have a doubling time, then it's going to double, right, base 2 every 5/3 of a year. So when t is 5/3, we get 2 to the first power, and we have that doubling time. So we can write it as base E for that relative growth rate model, but we could also write what's called a doubling time model if we wanted to as well, for those that are interested.